What happens when AI learns to reason about confidence, geometry, and 3D space all at once? In this episode, we dive into three cutting-edge papers: a transformer that refines human-scene interactions through geometric feedback, a new way to calibrate reasoning LLMs from just one unlabeled generation, and a vanilla transformer that surprisingly scales to powerful 3D scene understanding. From safer model predictions to richer spatial intelligence, these ideas show how small design shifts can unlock big leaps in performance. Let's explore the first paper: Graphed Geometric Refinement and Fitting Transformer for Human Scene Reconstruction. Graphed Geometric Refinement and Fitting Transformer reframes single-image human scene reconstruction as amortized geometry-based optimization. Instead of regressing a final SMPLX pose in one shot, it predicts interaction gradients, iterative corrective updates to pose, translation, shape, and scale, conditioned on explicit 3D scene geometry. The core novelty is a compact 2-4 token human scene interaction representation, where each token is grounded by geometric probes that query the nearest scene point, relative offset, and surface normal at body joints, hands, and full body anchors. A lightweight 5, layer 16, 2M. Parameter transformer alternates self-attention over these HSI tokens with geometry-aware cross-attention to map anything features from both the original and human-erased images, then reprobes the scene after each update, creating a recurrent physical feedback loop. This lets Graph function either as a standalone monocular HSI reconstructor or as a plug-and-play geometry-only prior that improves existing methods without retraining. Trained on inhabitants with 75K images and 97K human instances, using per-step supervision over a 3-iteration rollout and no explicit contact loss, Graphed achieves up to 113% higher contact F1 than feed-forward baselines and matches physics-level interaction quality at about 50 times lower runtime, 0.38 cetis versus 20s. On Rich, 100 and prox test, it raises human 3Rs. Contact F1 from 0.368 to 0.479 and from 0.268 to 0.387 inches geometry-only mode, and overall is preferred in 64.8% of a 5.3 participant user study. Let's explore the second paper: Unsupervised Confidence Calibration for Reasoning LLMs from a Single Generation. This paper targets confidence calibration for reasoning LLMs in the hardest practical regime: no labeled calibration set and only one generation at deployment. The core method treats test time self-consistency as offline weak supervision. Sample K responses on unlabeled prompts, use the empirical mass on the selected answer as a proxy confidence target, then distill it into a lightweight calibrator. In their implementation, the calibrator is a ridge plus isotonic regression model over response embeddings, with an external Gemma 3 4B IT embedding model working nearly identically in black box settings. Across Trediosac's model, dataset combinations spanning 9 reasoning models from Quintra, DeepSeek, RetDistill, and Nemotron on GS Modacoc, Polymath, SciQ, Trivia QA, and Web Questions. The method sharply outperforms token probability, answer token probability, and verbalized confidence baselines. Average ECE2 is 0, 89 over 0, 83 over 0, 76 for Quen, Nemotron, and DeepSeek families versus 0, 217 over 0, 191 over 0, 250 for token probabilities, and in the aggregate table it reaches ECE2, Breyer 0, 75 over 0, 102 on math, and 0, 97 over 0, 208 on QA. It remains robust under language and task shift, for example. On QA domain transfer, it attains ECE2 0.13 versus 0.28 for the best baseline. And with only 5 offline samples, it still cuts ECE by more than 50% relative to the strongest unsupervised baseline. Downstream, the scores improve selective prediction and reduce GPT-4o Mini's expected calibration error from 0.27 to 0.13 inches, a linguistic calibration setup. Let's explore the third paper: Volume Transformer Revisiting Vanilla Transformers for 3D Scene Understanding. Volume Transformer Volt revisits the unmodified transformer encoder for 3D scene understanding by converting a scene into non-overlapping volumetric patches, embedding them as tokens with sparse 3D convolution, and applying full global self-attention with a 3D extension of rotary positional embeddings. The key novelty is not architectural complexity, but scale compatibility. Volt stays close to VIT. Flash attention style design, avoiding UNet hierarchies, local windows, and handcrafted grouping used by prior 3D backbones such as MinQNet, Octformer, and PTV3. Although naive training overfits badly on limited 3D supervision, a data-efficient recipe combining strong 3D augmentation, heavy regularization, and hard-labeled distillation from a MinQNet teacher closes the gap. Under this recipe, Volt improves from 31 to 40 MIOU on ScanNet 200, whereas PTV3 rises only from 35.2 to 37.5. Volt's scaling behavior is the central result, with joint multi-dataset training on ScanNet, ScanNet 200, ScanNet++, and ARKit label maker for indoor scenes, plus analogous outdoor training. It outperforms domain-specific backbones and reaches 80.5 MIOU on ScanNet, 41.6 MIOU on ScanNet 200, and 82.2 MIOU on new scenes validation. As a drop-in backbone for SPFormer instance segmentation, Volt also sets new state-of-the-art at 82.7 map 50 on ScanNet and 47.5 map 50 on ScanNet 200. Efficiency is a second surprise. Despite global attention, Volt-B is reported to be 2 times faster than PTV3S and use 48% less memory, showing that vanilla transformers are practical for scene scale 3D when paired with voxel patchification and fused attention kernels. That's a wrap on today's AI paper highlights. Thanks for watching.